We're going to evaluate the iterated integral from 0 to pi over 2 of the integral from 0 to x of x times the sine of y dy dx. And I said we, but I meant you. Go ahead and pause the video, come back when you're done. Working from the inside out, we integrate the sine of y, and we end up with the integral from 0 to pi over 2 of negative x cosine of x. Y will be evaluated from 0 to x dx. Substituting x in place of y will give us x cosine of x, of course. Substituting 0 in place of y will give us x times the cosine of 0, which is 1. But there's a minus in front of the x cosine of y, so I've reversed the order of those terms. So we now have the integral from 0 to pi over 2 of the quantity x minus x times the cosine of x dx. For the x cosine of x portion, we need to use integration by parts. And that's actually the reason that I included this one in these videos. It was so that we could remind ourselves of integration by parts. I will let u equal x and dv equal the cosine of x dx, so that du is equal to dx and v is equal to the sine of x. Using the integration by parts formula, we then have uv minus the integral of v du. The entire integral then becomes x gets integrated to 1/2 x squared, and then uv is going to be x times the sine of x with a minus in front because of the difference that we had in the integrand. And then I went ahead and just integrated the sine of x. It becomes negative cosine of x. But remember, integration by parts gives us uv minus the integral of v du, and now what we have is a negative in front of negative integral of v du, so those two offset each other, but then the integral of the sine of x is the negative cosine of x. So keep track of those negatives. This whole thing is evaluated from 0 to pi over 2. Putting pi over 2 in place of x for 1/2 x squared gives us pi squared over 8. For x times the sine of x, since the sine of pi over 2 is 1, we end up with pi over 2 with a minus sign in front because that was a negative term. And then pi over 2 in place of x for cosine gives us 0. Putting 0 in place of x, 0 is out the first two terms, but don't forget that the cosine of 0 is 1. And our final answer, pi squared over 8 minus pi over 2 plus 1. Let's do another one. Evaluate the double integral over the region D of x squared plus 2y dA, where D is bounded by y equals x cubed, and we have that x is greater than or equal to 0. I do recommend, if at all possible, sketching a graph of the region D when we're setting this up. We need to figure out what our limits are on x and y. Well, y equals x cubed is the cubic function, and y equals x is, of course, the line with a slope of 1 that goes through the origin. They intersect at the point 1, 1, and we're only looking at the portion where x is greater than or equal to 0, so we're in quadrant 1. We could choose to work with y equals x cubed or x equals the cube root of y. It just depends on the order of integration that we choose. Looking at the integrand, x squared plus 2y, it's about the same either way. So I'm going to go ahead and identify this as a type 1 region. I said I don't usually care about that, but since you have the vocabulary, I may as well use it. And y is going to go from, in this region, the cubic curve, up to the linear function. So y goes from x cubed to x. And then our region goes from x goes from 0 to 1 for our region, is what I meant to say. If this reminds you at all of finding volumes using shell, disk, and washer methods, it totally should. Considering limits for a region D is very much like what you did at that time. Our integral is then set up as the integral from 0 to 1 of the integral from x cubed to x of x squared plus 2y, and we have set this up using the order dy dx. Integrating with respect to y, we get the integral from 0 to 1 of x squared y plus y squared. That's going to be evaluated from y equals x cubed to y equals x, and then we're still going to integrate with respect to x, so there's still a dx. Doing our substitutions, we get the integral from 0 to 1 of x cubed plus x squared. That's what we get when we plug in y equals x, minus the quantity of x to the 5th plus x to the 6th. That's what we get when we plug in x cubed in place of y. And we're still going to integrate with respect to x, so we still have dx. I have no like terms, just the power rule all over the place. 1/4 x to the 4th plus 1/3 x cubed, and then distributing the negative and integrating, we get minus 1/6 x to the 6th minus 1/7 x to the 7th. That whole thing is going to be evaluated from 0 to 1. The arithmetic there gives us 23/84 as the value of our integral.